Almost every culinary tradition relies on the same basic instruction. To improve the flavor of a dish, add a pinch of salt. But this creates a strange contradiction. Adding salt to a fresh tomato doesn't just make it taste salty, it makes it taste intensely like a tomato. We're taught to view taste as a simple matrix. Salt is categorized as one of 5 equal pillars, alongside sweet, sour, bitter, and umami. Chemically, however, salt functions as a structural overlay. It is a unique mineral that actively influences how our tongue and brain process the other 4 categories. Sodium chloride acts as a chemical modulator. It changes the physical behavior of our receptors to filter the signals we receive from our food. When those crystals hit your tongue, they adjust the sensitivity of your taste buds in real time, changing your perception of the meal before your brain even identifies the flavor. You can observe this modulation clearly in a cup of black coffee. Even a tiny amount of salt can noticeably change the experience of the drink. Normally, bitter compounds in coffee bind to receptors on your tongue, sending a sharp signal interpreted as a warning. But sodium ions physically interfere, crowding the receptors and preventing those bitter molecules from firing. Once that bitter signal is suppressed, the brain can finally detect the subtle aromatic notes that were previously buried under the bitterness. This same mechanism explains the popularity of salted caramel. In this case, the salt does more than just mute bitterness. It actively magnifies the sweetness. Sweet taste cells contain a co-transporter protein called SGLT1. When sugar and sodium enter simultaneously, the system activates, producing a massive sweetness signal. Additionally, water molecules clustering around sodium can mimic sugar, causing receptors to fire without sugar. On a biological level, salt is essentially a tuner. It mutes the bitter frequencies while turning up the volume on the sweet ones. Salt doesn't just change how we perceive the food, it changes the physical structure of the food itself. Salt is highly efficient at drawing moisture out of organic tissue. On the surface of a steak, this dehydration allows the high heat to create a dark, textured crust that wouldn't be possible otherwise. By pulling water out of ingredients, salt increases the viscosity of sauces and broths, making them feel more substantial as they coat the palate. Beyond texture, sodium interacts with organic compounds to increase their volatility. It makes the chemical components of flavor more likely to escape into the air. As you chew, these volatile compounds release from the food and travel upward into the olfactory receptors at the back of your nose. Since the majority of what we experience as flavor is actually derived from our sense of smell, salt is physically pushing the flavor out of the food and into our sensory system. This reliance on sodium has created a massive challenge for the food industry. While health guidelines urge a reduction in sodium content, replacing it has proven to be a significant engineering hurdle. If the health risks of excessive sodium are so well documented, why hasn't food science found a perfect substitute? The most common alternative is potassium chloride. On a basic level, it does trigger the receptors that register a salty taste. However, potassium chloride cannot replicate the more complex functions of sodium. It often releases flavor too slowly and frequently leaves a metallic, bitter aftertaste. Sodium is unique because of its specific atomic size and electrical charge. Its ability to interact with water and proteins is a specific property of the element itself. This unique chemistry is what makes salt such a powerful tool in a home kitchen, as the crystals dissolve and begin their work. The next time you salt a meal, you aren't just adding a seasoning, you are using a mineral that mutes bitter compounds, it amplifies sweetness, and physically moves the aromas of the food into your senses.